Okay, good afternoon, everyone. I'm happy here to present our recent work on the oblique northeastern Gulf of Aden continental margin using a 3D seismic tomography. This work is collaborated with my colleagues and now under review at GIL. Okay, now, so the continental margin are important to understand the continental breakup and the plate divergence on the Earth. And our study area, Gulf of Aden, is located, this margin located in the south of the Indian Ocean and to the north of the Indian Ocean and to the south of Red Sea. So in this margin is between the Arabian and the Somali plate. So this is the extension direction. And the rifting system is very young, only started at 34 to 17.60 million years ago. So, and you can see the strike of the rifting is oblique to the extension. This angle is about 40 to 60 degrees. And this margin, so it's highly segmented by the multiple fracture zones here. And in this margin in the west, it's a type of magma-rich continental margin because interacting with the AFA hotspot, and in the to the east, it becomes magma poor. And in this red box is our study area. So in this area, and there are a lot of geophysical surveys already in this region. So first of all, in this seismic reflection profile here, and we do not see seaward deeping reflectors, SDR. That means this is not a typical magma-rich margin. And from the magnetic data, we can determine the occurrence of the oceanic crust. So it's about at magnetic A5D at about 17.6 million year. So in this blue line, which is the onset of seafloor spreading by magnetic data, and the orange area can be identified as an continental ocean transition by seismic and magnetic data. So we can see there is a V shape, narrow in the west and wider to the east. And there's also a second order segmentation with second 1 to 3 segment offset by 2 lateral transfer zones. And in this segment 1, we can see in the seismic reflection data, there's a seismic, there's a seamount, volcanic seamount with very high heat flow currently. And to the east, segment 2 and 3, we have wider COT, and we have possible mantle accumulation by detachment fault. But this, all of this understanding is based on 2D seismic tomography or reflection data, and which is not enough to show the oblique rifting and the margin segmentation during the continental breakup. So my target is here is to do a 3D seismic tomography. The data was collected very early in 2006 during the Unsung cruise. There are 35 OBS and 13 land stations in blue. And there are 75 air gun shots along 15 lines. And our goal of this 3D seismic experiment is to investigate the oblique crust thinning of the continental breakup and the margin segmentation, and also to verify if there are any mantle accumulation and to look at the post-rift volcanism in this segment 1. Here I go quickly through the workflow. Actually, it's very classic. So the first step is to pick the first arrivals P wave like this, and then generate 100 random starting velocity to do the mental Monte Carlo analysis. And each starting model is used in the fast first arrival seismic tomography software to do the inversion. So after about six iterations, the chi-square reduced to almost 1 with a very small RMS of the travel time residue. So, and the final velocity model is averaged by 100 inverted model. Then I use the checkable test to calculate spatial resolution, which is less than 10 kilometer at about 12 kilometer below the seafloor. So before we go to the detailed results, we compare the previous 2D seismic profiles with our 3D at the same position. For example, this profile along crossing the volcanic seamount. So we first will focus on the near the COT. We can see the red line, which is the MOHO in 2D profile, and the dashed line is the 3D 7.5 kilometer per second in 3D. Because in our 3D model, we don't have the it's a first arrival tomography. We don't have the PMP to constrain the MOHO. So here we compare both the MOHO in 2D and the 7.5 kilometer per second in our 3D. So they are very close near the COT, and in other profile, we can see the similar pattern. Near the COT, the MOHO is comparable to the 7.5 kilometer per second. And in the shallow part, we can see some small features in both 2D and 3D. And in this profile, it corresponds to this volcanic seamount. But we can see there is a big difference between this 2D and 3D seismic data tomography in the continental part, because there is not very few seismic rays to cover the crust. So in the following, I will use the 7.5 kilometer per second as a MOHO to calculate the crustal thickness, which is in this map of the crustal thickness. So that the red color means thicker crust, blue means thinner crust, and here this one is the coastline. So this is Oman, and we can see from the continent to the ocean, the crust is thinner, and and we can see the contour of the crustal thickness here. It's almost parallel to the coast, and the strike of these contours, they are almost about 45 degree oblique to the spreading direction. So this is consistent with the original obliquity at similar angle. But this obliquity only exists in segment 1 and 2, but in segment 3, the obliquity is not exist. It's almost orthogonal 90 degree. And this obliquity can also be found in other crust layers. For example, this upper crust, we can see the similar pattern, and the lower crust, middle crust, we can also see the obliquity. And in the velocity slice, for example, this slide at 12 kilometer below the seafloor, we can see this oblique contour of 7.5 kilometer parallel to the coast. And also in the gravity data, the residual mantle Bogle anomaly. So all this data show the obliquity crustal thinning in this continental margin. But based on the magnetic data, the onset of seafloor spreading, this black line is almost orthogonal to the spreading direction. So that means there is the spreading direction is rotate, not the spread, the strike of the of the rifting is rotate about 45 degrees. And our interpretation is the obliquity may be accommodated by these two lateral offset in this dashed line, blue dashed white lines. This build the margin segmentation 1 to 3. And if we compare with the corresponding mid-ocean ridge here and here, here is the map. We can see these two segmentation have similar pattern, and they all have 3 segments, and the lengths of the segment are very similar with 2 offsets. So we think the margin segmentation could be inherited by the ongoing seafloor spreading at mid-ocean ridge.
Gee, it's 11 minutes.
Okay. And so if we look at along the continental ocean transition, we can see the crust here is 13 kilometers is thickest, and the thinner to the east at only 5 kilometers. So if we look at from the thinnest crust at profile 5 and 6, and here is the COT, this orange line, and we can see there is an elevated velocity beneath the COT, and if we take and this elevated velocity is kind of similar to the magma pole southwest Indian Ridge, 64.5 degrees east. At the foot wall of the detachment, they have a elevated P wave velocity. And if we take the 1D profile beneath this elevated domain, the red and the orange line, we can see there is a constant velocity gradient to the depth, and it's this range fall in the range of the serpentinite of the southwest Indian Ridge and the West Iberia, the rift magma pole rifted margin. And in addition, there is also a weak magnetic anomaly A6 here inside the COT. It's not caused by the oceanic crust because the signal is very weak, but maybe caused by the serpentinization here. And to the west, segment 2, in profile 3 and 4, in profile 3, we can see also there is elevated velocity, and also the 1D velocity correspond to the serpentinite. But in the profile 4, the shallow part, this red line, it has a similar pattern as previous profile, but there is a thicker crust. So there is a decreased velocity here, and here we can see the crust thickness between the seafloor to the 7.5. It's thicker than the other profiles. So maybe there is a later magmatic underplating here. And to the western segment 1, which is more complex, in the profile L2, here is a volcanic seamount, but nearby there is also an elevated velocity, which is maybe correspond to the detachment fault like previous profiles. But the crust nearby is about 10 kilometers. And here is a high heat flow. So, and in the profile 1, western profile, the crust is 13 kilometers. It's much thicker. That means there is a post later magmatism. So we have the 2 stages of the COT formation in the segment 1. In stage 1, there is a mantle exhumation by detachment fault, then followed by the post-risk volcanism in stage 2. But the source of the post-magmatism is not clear, maybe from the AFA plume or the small-scale convection after the continental breakup or during the early seafloor spreading. So here are the conclusion of the presentation with the 3 sketch. for the northeastern Gulf of Aden continental margin. First, we found an oblique crust thinning, which caused the margin segmentation and inherited by the ongoing seafloor spreading. We also found the evidence of the sink rift mantle excavation by detachment faults in all segments, and in the western segment one, it's followed by the post-rate volcanism, which emplaced into the cementinized peridotite, to build a composite crust like this. So that's all. Thanks, Messi.
Thanks very much. Are there any questions from the audience? Just put it in the chat or raise your hand. We can hear what it is. Yeah, there's a few hand raised. Sorry, let me see who they are. So Thomas, yeah, you go for it. Sorry, no question.
Yes, sorry. Yeah, I was about the resolution of your system. What is the distance between each receivers on average?
Oh, it's about 10 to 5 kilometers. You can read this about 10 kilometers. You mean the the distance between the OBS. Because it's very early cruise, so the OBS, and the OBS it's about 10 kilometers, and it's not very modern experiment.
Yeah, you mentioned that the crust was the distal geometry of the crystal thinning was oblique.
Yes.
To the direction, which is on also along the discontinuity where you have transform. I was wondering, can you really see if you would have like exumental or continental crust? Can you really see the difference between, continental material on exumental with this resolution? I'm just wondering.
Oh, because the crust here, the crust is about less than 13 kilometers. So our resolution in that depth is good enough to see the COT structure. But for the continent crust, it's thicker, deeper. That means the seismic ray goes deeper, and we cannot see the resolution in the continent part is not very good. So we don't give.
Yes, I understand, but I was just talking about the distal margin. If you would have exumental or continental crust in the transition from one segment to the other, so transform, can you really see that it's oblique or not if you don't have enough resolution to see the transition from the velocity you see in the continental crust and the velocity that will presume in serpentinized mantle?
Yeah.
So I'm just wondering if it could be a limitation of not seeing a transform in the distal margin.
Yeah, actually, I have so in the transform. So this is a transform zone, and we can see that it's a thinner crust than the margin segment. So maybe it's but it's not very robust, and we don't have a cross line along the transfer zone. Okay. But we have several profile like crossing in this direction, and we see the crust is thinner than the segment here.